Okay, boys, girls, fucking degenerates, it's day 6 or 7. Should be day 6 of No Nut November. We can't be looking at porn, so we gotta settle for these tutorials, right? Don't masturbate to these, that'd be fucking weird. But, what the fuck am I talking about? The prompt for today is paper, and I decided, you know what, why not make a crumpling thing, which is pretty symbolic because several months ago, I made a physics tutorial about how to do the same effect, and who would have thought it'd be possible to do the same thing with nodes? You know, stuff's evolving really quickly. So I'm going to show you how to make this animation, put a drawing on it, and have it deform with the crumpling. Of course, there is a bit of glitchiness going on, but it will explain why that is not very preventable and all that. So again, day 6, Nodevember, drawings. We're finally done with food. Fuck food. I never want to see it again. As always, blend file, which is already completed. This is the completed version with the drawing and the nodes in the node group. It's available on Patreon. However, we're going to do our best to recreate it. Why? Because I vowed that I would make a tutorial every day. That's why. So what is it that we're making? Of course, we're making a node group that does exactly what you saw. And the controls we have is, first of all, the transform. How transformed is this vector displacement? And yes, this is another vector displacement tutorial. Maybe next time I'll do something without that good old VD. But kind of like a toxic relationship. It just keeps calling you back and you just can't say no. We also have the crumpling, which only works if the paper's active, which kind of looks like realistic crumpling. Pretty proud of that. We'll talk about how to do that. We have the distortion level for the drawing. In other words, like this drawing right here, how badly was it drawn? Is this a drunk person, a kindergartner, or whatever, drawing this? And then we have some other stuff for cutouts, and that's just like the size and the position of these holes, etc. Let's get started. So we're using Blender version 2 point something, that's for sure. I think it's 2.9. I'm just going to set up the scene the same way that we've always been doing with an HDRI and vector displacement. So again, cycles, GPU, because GPU is faster, adaptive sampling. You should know this like the back of your foreskin. I don't know. You should know this part very well. We're just setting up an HDRI, shading workspace, go to the world tab, boom. I could do this blindfolded, one-handed. I could do this while like nailed down to the stake. Is that how they say that? While I'm being tortured is what I'm trying to say. So HDRI, I got one from HDRI Haven, same one we've been using every single time. Make sure that in your material settings, that the settings of the material settings, I know it's recursive, make sure this is set to displacement only so that displacement actually works, not displacement and bump, because that creates lighting artifacts, and that makes me and you a very sad boy. Okay, so what do we have so far? What we have so far is the scene with our default cube, HDRI, displacements enabled, and last thing we want to do before we save is add a bit of subdivision. And I guess we could do it with the cube. I'm actually going to start with the sphere. I forgot that's technically what I started with. Forget about it. If you want to start with a cube, that we talked about that 2-sphere transformation you can do at the beginning of the vector displacement chain. It's basically the same steps, but now you just have to take your cube, make it a sphere. Point is, let's give this thing a material and make sure that it's the same material so that we have, I guess we didn't, displacement only, okay? So how are we going to get from a sphere to a sheet of paper with drawing? It seems impossible. It seems insurmountable. We have a life's work ahead of us. Well, first thing we're going to do is we're going to take the sphere and project it onto the XY plane. So let's actually visualize that. And again, these are just steps of a transformation, one after another after another. First, we're going to use vector displacement to put this on the XY plane. I guess we're going to use UV maps to do that. We then want it to be a square, so it's kind of look like paper, like origami paper, except we're not going to fold it. We're going to do something else to it. We're going to make it a rectangle, and then we're going to do that crumpling thing, which has to do with projecting it back to a sphere. I'm rambling. Let's get to it. So again, step 1, how do we take this and project it onto the XY plane? And this is a trick we already talked about. To do this, first of all, we're going to set up our texture coordinates. Remember, not the brick texture, what the brick? Remember that generated coordinates are actually, it is the only fucking, there's all these coordinate systems, they all look eligible. Generated coordinates are the only ones that move with vector displacement. Who would have thought? So we actually want to start with this instead of object coordinates or geometry position coordinates. So what I'm going to do is I'm just going to transform this so we are still using generated coordinates, but they look like they are object coordinates, and that will make sense in a second. So I'm taking these, I'm going to shift them down by -0.5, and then we're going to take this, and then we are going to scale it by what? Not 1, not 3, but 2. And let's connect that right there. Okay, so what do we have so far? Right now we have a coordinate system that, if we look at our object coordinates, it's going to look exactly the same. These are indistinguishable because we took our generated coordinates. They use the bounding box of our object. So right now the origin is in the corner of somewhere in the bounding box. So we then shifted it over so it's centered, and then we scaled it so it's going from 0 to 1 on the x, y, and z axis, okay? So this is just going to be the coordinate system that we're using. We can tuck that away and forget about it like your hopes and dreams. Put that in the corner. Okay, cool. So first step is how do we, again, project this onto the plane? We're going to use UV coordinates. So I'm going to add another texture coordinates node. You could use this one from back here, but you know what? I don't want to, and you can't make me. We're going to take UV coordinates, put this in our displacement, which is going to give us a bad transformation. Again, why? Because vector displacement is a displacement. It's not the final position. In other words, we have the original coordinates, like the generated, or I guess not the generated, kind of like the position-based coordinates. We want to subtract those away because we want the displacement, not just the final position, okay? Hopefully that makes sense. If it didn't, maybe get smarter. I don't know. I've explained it many times. What we're going to do to fix this is we're going to do vector math. We're going to take this transformation. Again, we want it to end in UV coordinates, and we are going to subtract away the initial coordinates so that now it is resting on the XY plane. One thing you're going to notice is that this is looking like that cousin that you haven't seen in a couple years, and you're like, wow, you've grown like a mole, not a mole. But what I'm trying to say is it's looking deformed. A deformed cousin. You can fill in the joke there. The reason this is happening is we're taking a three-dimensional object. In topology, we say this has genus 1. In other words, it's the same thing as a cube, a pyramid, anything that is three-dimensional, not infinitely thin. And we're trying to compress it into, like, I think a genus 0 object, right? Again, we're projecting it to the UV map, which is a XY thing, right? And of course, it's not going to be able to do that because, again, it's three-dimensional. So what we're going to need to do is a bit of cheating. In edge mode, you are going to right-click and do edge split, which is going to take all these edges and disconnect them from each other, which is what is going to let us actually do our transformation. So again, before, we have this kind of deformed geometry, and after. It's like Instagram versus reality, okay? So again, reason this works is because the topology wouldn't let this transformation happen. So we need to make sure each face is acting independently. Okay, cool. So now the name of the game is making this, not doing that. That is absolutely not what you want to do. Name of the game is taking this and turning it into a sheet of paper that's usable. First thing that is the issue is you're going to notice that this UV transformation has the origin right here. So it's kind of starting at the corner and then going upwards. Again, this is because we're using UV space where the origin's in the bottom left corner, and then we increase on X, on Y, etc. So let's just do a tiny adjustment. We are going to add the vector, or in other words, subtract negative 0.5 on X and Y, because again, the origin was up here. So we just shift that down by negative 0.5, and now it rests here. And then I guess we could also make it look a bit bigger, a bit swoller. It's kind of like a dick pump, but for our vector displacement. Okay, take this, scale it, bring it up. Cool. So now we basically want to stay organized because historically I haven't been organized. So let's just take a second to organize everything. Remember that no matter what we do, all these steps for our vector displacement that we chain again and again and again, it should result in connecting to the subtraction node because, again, we are subtracting away the initial coordinates because it is displacement, not the final position. So what I'm going to do is I'm just going to give this a bit of color coding so that we don't need to zoom in every time and be like, which node is that? I can't see, right? I'm farsighted for nodes, right? Okay. So let's take this, make it a node group. We can call this node group coordinates because what does it do? It gives us our initial kind of UV transform. And then the next step is going to be taking this and removing those jagged edges. The reason that these jagged edges exist is it's to prevent area and angle distortion. And you can see this is actually our unwrap. In the original mesh, those are actually the poles, these triangles. They're like put up there like a fence or something. So our first objective is to get rid of those. To do that, what I'm going to do is I'm going to add in some separate x, y, z so we can look at only the y coordinate. Again, I'm not looking at the initial coordinates. I'm looking at the last active step of our vector displacement, and that is a theme that is going to be repeating again and again and again. We're just going to hit you over the head with it. What we want to do is isolate the top area and the bottom area and say do vector displacement here but nowhere else, okay? To do that, I guess we didn't save. That is a good point. I'm going to call it I have a Patreon because that joke's not funny anymore. Boom. We need to isolate those areas. To do that, I'm going to use a math node, if I can actually select that. And I'm going to set this to absolute value. Why? Because this automatically gives us some symmetry because the positive y values stay the same. The negative ones are they are made positive because they are negative and absolute value does that, which gives us y direction symmetry. This would work on any, axis. So here's x, y, etc. And we need to now isolate that area. A quick way to do this with a gradient that isn't like a cutoff, right? With like a greater than, less than is always this map range node. And what we want to do is kind of isolate these areas. To do that, I'm just going to bring up our like bottom threshold, just so we're isolating it a bit better. And I guess the closer we get to this, the better, since we don't want to do, again, oh, the burps are coming. I ate too many beans today. Chipotle is ripping through me like a shark rips through, I don't know. We're trying to isolate this area. So I'm bringing up the center area so this isn't transformed. These vertices are going to stay the same. And to make sure that our gradient is actually starting from 0 and going to 1 on each of these, I'm just going to bump this up. So it's going up to like 3 or 4 or something, okay? And you can see whenever we do this, it's getting brighter. So now we have made a mask, and now that we've made our mask, we know that we want to keep the center in the same spot. But now the question is, what do we want to do to the top and bottom? What is the fate? We're the jury members. We can choose what we want. To do this, what we're going to use is a simple function of basically taking this section and say map it up to y equals 1. And the bottom section, map this to y equals -1. Well, there's actually a math node that does that. It's called sine. Not sine as in trigonometry, but sine as in kind of like, is it a positive or negative? It outputs 1 if it's positive and -1 if it's negative. Okay? So we're just going to hook this up here. And now that we have our kind of resulting map, again, 1 if it's positive, -1 if it's negative in our mask, what we can do is actually create our displacement. So we're going to mix RGB using our factor, this map range. We're going to say wherever this is white, or at least not black, which is the bottom socket, we're going to say use the sine thing, and then otherwise just use the y coordinates, right? Because we don't want to transform them. I mean, you could do 1 or 0 depending if you're adding or multiplying, but we could do this directly with separate and combine x, y, z. It's always best to get straight to the source. It's kind of like the vegan philosophy of food. Minimize those steps in between, and allegedly it's healthier. Okay? So what we have is, again, our y coordinates, but it's kind of hard to tell. We have a bit of clamping going on for the top and bottom. Meaning what we can do right now is combine x, y, z. So again, we took our initial vector displacement, separated it by components, did some magic, and now we want to combine it. So x is not being affected at all. We can connect that. Z-axis, we can do the same thing. And then for the y coordinates, those are exactly what it is we're transforming. So just connect this right here. And now, since we have a new vector displacement final step, we connect it always, every single fucking time. We connect it to the subtraction, which gives us this, which is almost what we want, but not exactly. You can see that there's still a bit of stretching going on here. And to fix that, what we need to do, first of all, I need to make sure that this is correct. It should be correct. Yeah. What we need to do is basically increase these values or change our map range node until it does what we want. So again, if the gradient is like not harsh enough, it's not going to work. So I think lowering this is what we want to do this time. So now it has a more gradual gradient, so it has time to build up, and that makes it look more like a rectangle. For those of you who are hands-on visual learners, you guys were always my least favorite, but for those of you who need that, here's actually what's happening in the geometry. You can see that we have stretched the top and bottom, which does mean, yes, we have less geometry on the top and bottom. However, the more divisions we have, we still gain some of that geometry back, so it's not a big deal, okay? Nice. So next step, what are we doing? I guess next step is kind of reforming this a little, just so it's the aspect ratio of paper. I mean, I guess this is pretty close, but we could do a bit better. So I'm just going to move this down, and I think we can make this another node group. So just select all of this, and this is now the next step, Control G, and now we have a second node group. We could add some parameters, but I don't think we're going to be going back to this, okay? So for this one, we are going to call this, I guess, edges or something like that, because we made it a rectangle, we fixed the edges. Okay, now to make this longer, kind of an easy operation, math, nope, not math, because again, we're dealing with vectors. Vector math, set this one to multiply 1, 1, 1, so nothing's affected, because again, when you multiply something by 1, what do you get? You get itself. So if we take y-axis and increase it, now we're getting a longer and longer paper. And this might be something you want to turn into a parameter someday, but I'm not going to. In fact, what we can do is actually copy this. So I'm Control-C'ing this node. And let's actually put it inside this node group so we're not like adding unnecessary node groups. So Control-V, should be somewhere here. Here we go. Connect it. Boom. Not boom. Boom. Now it's all inside our step. So again, what we have right now is we took our sphere, we mapped it to the UV coordinates, and then we did our scaling and edge work to clean it up. Okay, next step. I mean, I guess in some sense that really, it really is all the modeling for the paper, but now what we want to do is assume we've already kind of put the lines and all that, and I'll talk about how to do that. So again, imagine we already put this design, the drawing, the red and blue lines and everything. The question is, after we do that, how do we do the crumpling? And this is the part of the vector displacement part of this tutorial that gets pretty new, it gets pretty novel, so take your eyeballs and clamp them open, okay? To make it look like it's crumpling, of course we can't make it like physically accurate because that needs self-collision physics, so we know that the paper doesn't pass through itself. We can't do it very well, but we can help it do that, right? So we can kind of guide this to looking like crumpled paper. So what we need to do is, I know we spent all this time making it flat, but now what we need to do is take this and kind of return it to a sphere. And we can use kind of like the inverse transform of this, or we could use something cleaner to do that. So we're going to kind of wrap this into a sphere and then add a bunch of noise so it looks crumpled, okay? To do this, here's kind of a kind of cool thing I came up with. We're going to use vector math, and this time we're going to use a new function, distance, which outputs the distance between two vectors. You can imagine 2 points in 3D space, and you're asking, okay, what's the Euclidean distance between these, okay? And this is what it outputs. So I'm going to use a combine XYZ just to make this separate. And again, this is going to take our coordinate system that we've now adjusted so it looks like it's a plane on the plane, etc. And we want to output the distance between this and a custom vector. I want you to imagine that we're going to take this and wrap it on a sphere that's lying above the paper, so like 0, 0, 1. Imagine that there's a point at the top of the sphere, and we want to wrap the paper inwards, okay? So now we have computed the distance between these. We're going to get a kind of very, very soft gradient. You can see it a bit better if we did a kind of like a greater than or something. So you can see it's kind of like a sphere cutting into this effectively. We now have a distance function, and we want to say, Blender, hey, wake up, buddy. Slap, slap, slap. Project this onto the sphere. To do that, we need the vector of the resulting sphere. And the way we get that, and this part is admittedly a bit confusing, we need the vector that's kind of like projected from this point onto the XY plane. And I understand how the fuck are we going to get that? I'm not the whiz kid, right? The way we get that is we just use a bit of vector math. So this vector right here is actually just the position vector on the plane minus this 0, 0, 1 vector. Again, I guess I could draw on the screen. This vector that we want, which is what we're going to use to project onto the sphere at this distance, right? This vector, we'll call it x, is exactly this one minus this one. What do we know about this? We know that this is the 0. Dude, I feel like such a fucking loser using the annotation tool. I know Aaron does it, I'm not calling you out. This vector is the 0, 0, 1 vector, and this one's the position of the point on the plane. In other words, this last vector displacement step, we subtract these, we get this, and then we scale it. So it's actually not that bad. Annotation tool's pretty useful. I think I should use that more once my computer handwriting gets good. It's really hard. I feel like I have shaky hands. It's hard to control that, you know? Okay, so let's do that vector math. We are going to use vector, another vector math node, set this one to subtraction again. We said it's our position vector minus whatever our point on the sphere vector is, so that's this one. So now we have this coordinate system, which it doesn't look very different, but just, hold your horses. What we're going to do is we're going to scale this by what? By the reciprocal of the distance that this already has again. What defines the sphere is it's the set of points that are equidistant from another point, like a friend group that's equally liked by a single person, kind of, but not at all. Meaning that if we have a bunch of distances, we want to normalize them to 1, and that can be done by just multiplying by the reciprocal, or in other words, taking the reciprocal, okay? So what we are going to do is we are going to use a math node, because again, now we're dealing with float stuff. Take this, divide reciprocal, boom, boom. So now we have the reciprocal of the distances away from this point. Again, we're talking about this vector. What scale should that have? It should be this. And then we take these projection vectors and we scale them. And I understand this is a complicated idea, but just watch the magic happen. We connect everything here. We connect it to the subtraction. And now you can see it's kind of mapped to the to kind of to the confines of the sphere. Again, this works because of all that vector math from before. We normalized the correction vector and said this is the new coordinate system. And this gives us quite a bit of control. We can control the radius of the sphere. That's not too interesting, but what is very useful, let's actually make that 1 again. What did I do? Did I get rid of the node we need? Why did I do that? There we go. Now we got it back. We can control the radius, but what is more interesting is we can control what point are we projecting from. So we can make it very low. In other words, it's going to be projecting to a point that's very, very close to the plane, which makes it closer and closer to a hemisphere, which of course means we need more geometry. By the way, quick tangent. Have you ever thought about if you were in space and you're trying to like look at all of Earth, the best you can do is kind of go infinitely far away, and only then are you going to see half the Earth, because you're kind of confined to your perspective, and there's kind of like a limit. So whatever, take calculus, you'll find out that the further away you go from Earth, the closer you are to seeing half of the marble. Similarly, the closer this gets to 0, the closer we get to a hemisphere. And you see how that analogy would make sense if I knew how to fucking string a bunch of words together, but it's really poetic. So this is what gives us the hemisphere. And we we could do a correction to this. So right now what's happening is if we were to mix this together with our original coordinate system, in other words, so let's mix. In other words, we're saying how much of this transformation should happen. You can see what's happening here is we get our transform, but it's kind of dipping down, which isn't really how you crumple paper. Paper doesn't fall and crumple. It kind of like is pinned at the center. So in other words, we need to bring it up, and we can do that. But that's exactly what we need to do. So for this one, and this is again the chain of nodes that gives us exactly our hemisphere. For this one, what we need to do is add, I think literally the vector 0, 0, 1. We'll see if that's the case. Yes, because before it was like -1 down because of the whole projection trick. And now it's brought back up. And again, the more geometry we have for this stuff, the better it's going to look. In fact, let's go to an experimental coordinate setup right here, adaptive subdivision. Once that loads, let's bring that down. This is just, by the way, if you don't know what this is just going to give us the geometry based on the dicing scale. So the lower we make this number, the more subdivisions we have per pixel in some sense, okay? And if we move this further away, we're going to get cleaner and cleaner geometry because the projection isn't as harsh. And by the way, I don't think I mentioned this. For you fucking Nodevember veterans who are also no nutting, not shaving, and not eating sugar, you already know that. I think a couple tutorials ago, there was a bet about sleeping on the floor in the bathroom and all that shit. That's what's going on now. So if I sound like there's a gun to my head, it's because there's a gun to my head. Somebody's about to pull the trigger, send help. So I need to nail it on this take. But now we now have a factor that we can control with a value node. Boom. And this gives us either, I guess we should invert this because this isn't making much sense. We're at 0 here and 1 otherwise. So let's do a bit of an inversion. Math, subtract 1 over, boom. So when this is 0, 1 minus 0 is 1. And otherwise when this is 1 minus 1 is 0 is what I'm trying to say. What this does is it gives us one slider that uniquely gives us this transformation, which is pretty cool. And in fact, if you wanted to make sure that it doesn't go above 1 when we do this, you could do some map range node action. But quite frankly, I don't care. Same thing for like lower than 0. But it doesn't seem to actually be doing anything too harmful. Or we could clamp it. Okay, so now we have this transformation. I'm going to put this over here, and we're going to use this as a exposed parameter. In fact, you could also use this as an exposed parameter. We wouldn't really adjust this, but you're going to see that in the resulting kind of thing, it's going to give us what? Different kinds of crumpling. So let's take this, boom, Control G, and this is our crumple vector displacement step. So I think we can get rid of these. So let's rename this to crumpling, because what is it? It's a crumpling node, boom. Make sure this is the 0, 0, 1 vector, and now we have a nice slider, which this time I think we can actually clamp because it's a node group, so value, we're going to have it min of 0, maximum of 1. Boom. I love it when it all comes together. Now I'm seeing that this is, oh right, we don't want the 0, 0, 1. I just did this whole spiel and forgot about it. One kind of side effect of this is, again, depending on how far away from the Earth, how much of the sphere can you see, this is going to wrap it more and more around until we get to the limit of exactly a hemisphere. So I'm going to set this to 0.03 for now, maybe even a bit higher so we get a bit of extra geometry. so the projection isn't so harsh. And the point I was making is now we have a single vector displacement node that gives us our, I mean, is it crumpling really? Maybe it's more like sphering. I'm going to rename it. I know you guys were foaming at the mouth, dribbles falling on your desk. You're saying, no, that wasn't crumpling. That was projecting to a sphere. Now we could do the crumpling step. For the crumpling, again, we can't do anything too sophisticated because, again, we don't have like any clever way to avoid self-intersection. You could set this up mathematically to do that, but it'd be fucking nerdy. We're not doing that. We're keeping it simple. In other words, we're just going to add a noise and hope that it helps. Before we add a noise, just to make it look a bit more crumpled, we now have this hemisphere look, and it might help to pinch the top just a bit, because otherwise, let me just show you what's going to happen. We're going to add in a noise texture. We're going to mix these together, set it to linear light. We'll talk about why we do all those steps in a second. But when we use the XYZ, not the factor, you're going to see it does crumple this pretty significantly. But what makes this kind of look like a bowl of soup and not crumpled paper is the fact that we don't have this compression and pinching, right? So we need to do that before. So it's not just crumpling a hemisphere. That's what makes it look weird. To do that, we're just going to use kind of like the same tricks from before. We're going to separate by XYZ. We want to say as we go upwards on the Z-axis, we want to pinch the X and Y axes. So radially pinch it inwards as we go up the Z-axis, okay? To do this, no big deal. We're going to do vector math, not transform. That's a node I don't touch. I don't dare think about world space versus like Blender space versus like object space, normal camera coordinates. Forget about it. We're going to take this. We are going to multiply it by what vector? By a combine XYZ, so we can control the components. The Z should remain the same. I guess it should be 1 so it doesn't transform. And the X and Y we are going to determine. To do that, we need kind of a pinching map. We're going to use a map range node to do that. And what I'm thinking is the higher we get, which is kind of like already what we have, it should be getting brighter and brighter and brighter. Brighter and brighter and brighter. So that the amount of pinching increases, or should it be the opposite, so it pinches to 0. I'm thinking that maybe a 1, 0, so we flip this. So in other words, the higher it is, the larger the value, or sorry, the smaller the value, the more it pinches. Let's just try it out. I'm rambling because I don't know what's actually going to work. Let's try it like this. Boom. Make sure this is the newest vector displacement step. And there we go. Now we have this nice pinching. This is like the thing on top of Bulbasaur. If you ever want to make a girlfriend happy, get her a Bulbasaur flower. So we have the pinching. We can make it smoother by turning this linear map range to smoother step. This is going to give us, now it's really looking like a piece of garlic, clove of garlic, or the Bulbasaur thing. Or like that. You ever see those Russian palaces, those things at the top? I don't know what they're called. They're kind of like, you know how like every synagogue, church, oh God, I shouldn't get into religious shit. Some buildings have a golden cap at the top. Russian buildings have this thing at the top is what I'm trying to get at. If you're offended by this, just know I don't know what the fuck I'm talking about. What we need to do is make sure it doesn't pinch perfectly. Let's just step away from that little tangent. To do that, we are going to move one of these sliders. I think it's this one. Here we go. And now the map range kind of goes beyond. Long story short, we're changing the interval so it doesn't go all the way to 0 at the top so it doesn't pinch, okay? So now we have our crumpling, and this should be an exposed parameter since, again, it's going to control exactly, I think it was a 1.35. It's going to control exactly this pinching thing. This is radial on the X and Y because we connected it here, and again, we're multiplying by Z is equal to 1. Okay, so now we can take this. And again, the way I do this, by the way, if I haven't mentioned, shift right click drag is the way you do that. We want to take all these, make another grouping. So before we had our 2 sphere, here we have our pinching, and we should be getting really, I know, vector displacement takes forever. Now we should be getting really close to the kind of last step of the vector displacement, which of course is getting rid of this. I don't know why we have this here, which of course is adding in the noise just like before. So what we want to do is add a bunch of organic crumpling. In other words, we want to do a mathematical expression that's too complicated. So in these scenarios, what you want to do is always use one of these orange boys, some kind of texture, whether it be wave or noise or magic texture, or there's others. What are the others? Gradient texture, stuff like that. Noise is going to quickly give us the deformation we want. We just control shift right click drag to mix these two together, make sure it's X, Y, and Z. And again, this gives us our crumpling, which is easier to see like this. It gives us our crumpling, but you're going to notice that it's shifting everything up by the vector 0.5, 0.5, 0.5. Why do I know that? It's because, in some sense, what we're doing right here, actually now it's 0.5, 0.5, 0.5. In some sense, what we're doing here is mixing, but you can think of it as adding noise, which means at every point we're adding some vector between 0 and 1 on each component, which means on average, right, on average, when you take all these things and get all the data, you get your sample size 30 for your statistics analysis, statistician analysis. I took a statistics class. I don't know why I can't say this. On average, we are adding the vector 0.5, 0.5, 0.5. So we need to correct for it. In other words, we need to subtract. And this is one way to do it. You could like add this in and mix it with another vector. So you could do a subtraction. Does subtract exist here? It really should. Yeah, subtract by the 0.5, 0.5, 0.5. Or I guess maybe a different value depending on your mixing factor. You're going to notice it changes, and that's going to center it. All that math can be pretty complicated, especially when you change this mixing factor. Luckily, linear light, and I've gone on this spiel before, linear light takes care of this transformation for us. So you can see we now have a slider to control how crazy do we want this to get. Okay? And no matter what we pick, it's always going to stay centered, and that's the nice thing. So now, really all we need to do is just kind of decide what kind of noise we want. Do we want it to be detailed, so it's super crumpled? And yes, this is procedural, almost physics-based kind of stuff. So how crumpled do we want our paper to be? Should it be very rough? In other words, should it be super jagged as it does this or not? These are all things we can decide. But now we have a nice slider for this, and of course, just like we had a value node for the sphering, so when this is set to 0, we have paper. We don't want it to be crumpled at this step, and as it goes to 1, we want it to be crumpled. Of course, we just do that by connecting the factor. So now we have a nice way to crumple our paper, which is pretty cool. You're noticing that it might be getting a bit bigger because I guess it's kind of a big hollow shell. If you want to fix that, again, all you need to do is some vector math, some scaling, and it should be at the origin or near it. So let's see, we set this to 1, and now we scale it down. Boom. There we go. Now, I guess the issue with doing it this way is this is also going to scale down the paper regardless of what this value is, because again, it's at the end of our chain. So if you want to do this correctly, I guess what we should do is kind of like add a vector that's factored by this. If we are doing this 100% correctly. So what I'm thinking is let's try to do this in a very smart way. We're going to bring this all up here and the scaling, and we are going to mix this with the original. And we are going to use this again as a factor. What is this going to do? It's going to say only kind of progress down this chain, because again, we're mixing it at the very end, only progress down this chain as this increases. In other words, if we were to make the scale very big, I don't think it should affect the paper. Oh, it totally does affect the paper. Forget what I said. Clearly that doesn't work. Is it because the mixing? Whatever. Forget about it. Can't do it on the fly. We'll just skip that step. Point is, at some point in this chain, you need to add in scaling. I really do think it should be that thing from before. I guess I'm just forgetting like a very small detail. Is it just like switching these? That shouldn't matter. Does it matter? Let's see. Set to 0. And now, oh no, that actually is what it was. So now if we change the scale, you see it doesn't actually change our paper. However, it does change the crumpled result. So you can change the size of this ball, which is pretty cool. So let's do something like 0.65 and also manipulate. Again, we can always change our noise to get different quality of distortion, something like that, just so it looks super crumpled. And I know it's looking hollow, but you can fix that again with and this is what I meant from before with the quality of our crumpling. We can do that two-sphere projection, which is going to give us different states of the crumpled thing. So this is like you crumpled it, but you didn't fully close it and whatever. You could do that and also change your pinching factor to kind of make this a bag that's closed and stuff like that. And all that together is to say we've now crumpled our fucking paper. Let's go, boys. Final step is adding in our paper-like stuff since we've done all this transformation. And that is actually some of the easiest stuff since it's just classic XY manipulation. So let's just do that super quickly. So I'm just going to put this all here. I guess really we should put this in a group. So let's just do it like this. Control G. You could always expose variables because you would want to go back and change the noise quality and stuff like that. But for now, just forget about it. This is going to be our crumpling. Control C, Control V. Boom. And now, again, what we want to do is put our design on the paper, which is what is going to make it look like paper. This part I'm going to go through super fast because it's super easy. We can actually use a original coordinate system before we do the crumpling because, again, since we use generated coordinates very intentionally, by the way, since we use these generated coordinates, the benefit of that, and again, we used it here, is the transformation, our noise and all that, it transforms with it. So you can see how this coordinate system is kind of moving with the whole pattern. This is to say whatever we do based off this step, even if it's only the second step, is going to carry down the chain. And yes, you could do it as the fifth step, but it's kind of hard to mess with crumpled paper. I mean, the vectors and all that, right? Because it's all messed up. So it's easier to start off simply and then let the projection just ride the fucking wave. You're in California. I need you to picture this, okay? You're at California. You're at the beach. The waves are crashing down. Your hair is flowing in the wind. You're feeling good. I forgot what the fucking point was, dude. Point is, you want to start on step 2, and that's what it was, and flow down the chain. That's the idea. So let's do some stuff over at the second step. What we can do is separate X, Y, Z. And here what we're doing is adding in our blue lines. So let me just show you what I mean. I think you know what paper looks like, right? So the blue lines, those circles, which we're going to be able to control, the red line, and we're going to do a very quick drawing. Not a big one because that kind of takes a bit of time, but I'll show you how to do it. First of all, we want to make our blue lines. To do that, we want to separate to the y-axis since it's going vertically, so we need that gradient. What I'm going to do is I'm going to, first of all, add in some math so that we don't have any negative values. We're going to add 1, so it should start at 0 and go up to 1. And this is going to be a whole bunch of modulo stuff. If you don't get it, I was going to say, just think about it a bit, but really what I mean is that. Just think about it a bit. I'll try to explain it. So again, we've mapped this gradient from 0 to 1. We are now going to do a fraction command, which is going to say kind of forget the integer. I guess this was 0 to 2, which kind of illustrates the point. Instead of going like to 1 and then going beyond, this goes back to 0. It only keeps everything after the decimal place, which means now if we add in a multiplication, we are now able to control the number of kind of divisions, which we're going to turn into lines, okay? So fraction is the command that lets us do that. Again, it gets rid of the integer parts. We only care about everything after the decimal. We can take this, add in something like a greater than, less than, or even faster, a compare node. We're going to compare to 0 and just increase that a little bit. So you can think of this as your line thickness and this as your line kind of offset, which does take a second to update. I guess to make it faster, you could get rid of some of this vector displacement just for now, so that the result's still the same before crumpling, but we can now visualize this a bit faster. I guess it doesn't update that much faster. Forget about it. We'll connect it like this. This is going to control the offset, and this is going to control the thickness of the line y, because now we have this repeating gradient, and we're saying take this, compare it to the value 0 with a threshold of 0.09. In other words, how close is this gradient to this number, or which points on the plane are within this distance, this radius, this strength, this ganus, this desire of whatever value we are using. This is what's going to do that. We have this line map, which again, we can update procedurally. We want to say don't have the lines everywhere. It should start kind of like 20% of the way down the page. To do that, again, compare node is the useful one for this. And I guess this should illustrate the point a bit better. We're comparing to 0. This is kind of like the offset, as you can see. And then the epsilon is the radius. So I'm just going to isolate the bottom of the page like this, so we have a nice mask. And what I'm trying to say is have the lines only in this white section, so not at the top, kind of like the header. You guys probably went to school, are in school, or maybe you're hiding. Maybe you just don't go to school, I don't know. Fucking degenerates. So now we have our lines. We can control that procedurally. So that's one map, and then another is going to be pretty much the same thing, although simpler. And this is going to be our horizontal, so I'm using X, since we want that left to right gradient, right? And what we're doing here is, let's make that way smaller, is we're just going to make a line that is essentially the same thing. And we can just borrow this epsilon, this radius from before. I guess that was too big because of the gradient scaling that we didn't account for. Let's make that a bit smaller. And then again, just transition this down. You can always adjust this on the fly later on. Something like that. So now we have our blue lines and our slightly thicker red line. And to actually have this be displayed on our paper, Again, now that we've done all this vector displacement stuff, which let me just Shift P to put that in a frame. Now that we've done all that and we are working on our masks, pretty much the name of the game for the rest of this is BSDF stuff. So we're now on surface properties, not displacement properties. To do this very quickly, you just mix RGB, have like the color paper as the bottom socket, and let's start with our blue lines as the, I guess when I say bottom socket, I mean the one that is beneath in the sense of layering, not which one's physically on top of the other. The other one's going to be blue. We are going to use this as the mixing factor. Again, this is our blue line map. Take this, connect it to base color, find out it's inverted. Oh, I think I put it in the wrong socket's the issue. Factor. There we go. Now we have our blue lines, and to add in the red line, again, mix. Basically, these tutorials are self-explained at this point. You just kind of repeat steps over and over. Now we have our red line that we can control, the thickness of, and all that jazz. I wanted to make it smaller. Times 0.65, so 65% of the thickness. And again, the nice thing about this is since the factor was calculated on step 2 and it's based on generated coordinates, the whole idea of this whole thing is it moves with the displacement. And that's within reason, right? So if we were to increase this, you can see it's kind of distorting with it. Some lines get thicker and smaller, and this is something I've been trying to solve. Technically, I did solve it a bit. The reason this is happening is because of the noise and the linear light. If you want to solve this, I don't know if this is going to solve this or just make it manual, but I guess it's worth trying because I wasn't able to solve this on the initial thing, but just here's how you might approach it. Instead of using linear light, what you could do is do this manually. So again, we're going to do vector math addition, which is going to give us the right thing, but it's going to offset everything to the corner. So what you do is subtract by the 0.5 vector. Basically, I'm showing you what linear light does in hopes that it helps. I don't think it will. I think the issue is that adding noise is a non-linear transformation, which means some areas get kind of deformed. The area increases and decreases, which is why you want to do it in a mathematically precise way, not just adding noise, but I'm sure some nerd in the comments knows how to do this. We take this, we scale both of these, and we add in a value slider, just so you know how it works. And what this lets you do is kind of control the linear light slider manually. And in some sense, this is a bit better because it's less computationally expensive because we're kind of doing the calculation by hand. But sadly, it doesn't solve the problem. Again, the reason this happens is it's a non-linear transformation. So I'm just going to undo that so we have a cleaner node network. Hopefully there's enough undo steps to get that back. Let's see. There are not. Big sad, big sad. So what we need to do, mix RGB, duplicate, throw that in there, mix it with what? The noise set to linear light with a factor of this is what it's going to need. Did I do this correctly? It's off to the corner for some reason. I think the reason for that was we need to connect this to the mixing factor since we messed that up. Boom. Now we can again control this procedurally. Let me just connect this back to where it was. What was my point? The point was that within reason, again, there's that non-linear transformation issue for now. Within reason, you can see this actually transforms with our deformation, which is pretty cool. So now pretty much the last step here is adding in our transparent stuff, and you could add in a drawing. I might do a quick one, we'll see. To add in a circle, what I've taught you how to do is use some vector math and use length and stuff like that to generate a circle. The issue with that is I don't think it should transform with the thing unless we do some vector math, but you know what, let me just do it that way. It's cleaner. In my actual project, I did the actual formula for a circle, like x squared plus y squared square root to find the radius. What we could do is calculate the length of this. So let's just see that right there. So this kind of gives us a radial map. Again, we use math. Nope, not material output. We use math, set that to greater than, and now we have a circle. So let's make that smaller and also less than. Right there, something like that. And then to transform that over, what we do again is since it's based on this coordinate system, we add in a vector, connect that right there, to the left and all that. And I think, let's just make sure, I think this should move with the deformation. Yes, it seems to be moving with the deformation. This is how you get a very quick circle. Again, what we do is we add in I guess, transparent BSDF is a quick way to get transparency. Who would have thought? Boom, connect this here as the factor, and now, now you put it in upside down. Flip those. Now you have a dot that you can control procedurally. So again, what do we have? We have a slider right here that lets us control where it is, and then a slider for how big it is. And I guess we do want 3 of these, so let me just very quickly show you how to do that. We're going to duplicate, I guess, the whole thing 2 more times. So boom, and then boom. Put that off to the side. Connect, connect. And for this one, we just need to move one of these up. And we need to make sure that we're adding everything before it reaches our mask. So I'm just adding 3 different independent circles together. We just slide these around so there's a dot there and a dot there, etc. You could position these mathematically, and I did that for the final result. But for now, this is just going to have to be good enough. Okay? Boom, you have dots. You could position them elsewhere. For the drawing, you pretty much do literally the same stuff we've done, any kind of compare. I think my drawing, you might have not noticed, but very intentionally it was made out of simple shapes. So here we have a circle, a line, another line, and this is actually kind of a modified sine function. All of that can be made on the fly. Let me just make one of those very quickly for you. I'm thinking let's just adjust these dots because they're looking like garbage. So this one should be here. This one should be here. Boom. And let's see, make sure everything moves with our deformation. Yeah, that's looking really good. Okay, so for the drawing, kind of like last step, what I'm going to do is a very quick kind of like circle drawing. I don't know what dumbass kid out there is like drawing circles. Probably biology majors. But to do that again, exact same process. Length node, connect this here. We're going to this time use not a greater than, since we want not really a circle, but more like a donut. This time we're going to use compare, but this time radially, which is the difference between those lines and the circle we're doing right now. This time this is going to be the radius of the circle, and this is going to be the thickness of it, because again, when you think about all this radially, again, the whole idea here is we are comparing the radius, this is the length map, the radius, to some set radius 0.5 and saying which points are within this thickness, this epsilon away. Okay, so let's make that thin and smaller. This is going to be our drawing. And then finally, before this reaches the transparency, I'm just going to add in another principled, mix this together. This one's going to be black. And where's our map? It's getting confusing. It is here, the compare. Use this as the mixing factor, and that should give us our drawing. And then you just kind of keep on stacking shapes. But the key takeaway, and this is something that will add a lot of realism to whatever drawing you're doing, because people don't draw perfectly, you could do the same displacement trick from before, but this time in, I guess in 1 dimension, so after the length operation. You take this, you mix it together with the length, make sure this is set to color, connect it in here, and just like last time, we're going to get, at least we should get the displacement off to the side. That is looking mighty bad. We want to make sure this is set to linear light is the point. Should we have done this before? Yeah, I guess we should have done it before. So let's do it like that. Or what was that the issue? No, I think the issue is what we were comparing it to. There we go. I was right. You guys were wrong. Fuck you guys. This noise is, again, going to use the linear light operation to say, okay, when it's 0, don't account for any noise and don't do a correction, but we can increase this just a tiny bit. And you're going to see it's going to add some natural wiggle to our thing. So there we go. I guess we want our BSDF for this one to be a bit shinier because it's graphite, one of those. It's a bit shiny. And you can also use a noise as the mixing factor. You can multiply by that. But other than that, I am thinking that that's kind of the essence of the tutorial. Now you have paper that crumples and all that. I guess we need to see the last mix shader to get that. We now have paper that started off as a gist, and don't forget it started off as a humble sphere. We unwrapped it, did some 2-sphere operations, stuff like that. And most importantly, we did the crumple animation, which again has some deformation issues. One thing you could try to see if it's better is you can try different spots in the chain, which shouldn't affect the results here, but it will affect what happens during crumpling. So sometimes it's sometimes it's a bit unavoidable because again, these maps aren't necessarily linear. So I'm just going to try a couple of these. See if any of them. I guess this one works pretty good. Yeah, that one kind of sticks with the deformation. I guess it's because it's before the pinching and all that. Point is, now you know how to make crumpled paper. You're evolving. You're getting smarter. You're getting smarter every day, I guess is a good way to put it. And I think we've been going for a while, and I'm over it. I don't want to talk about day 6 of Nodevember anymore. So, yeah, if you want the original blend file, it exists. It really does over at the Patreon. You could get the unmodified one with all the sliders and everything. On top of that, that's where you can get exclusive tutorials. You can get Discord access. You can get behind the scenes. And quite frankly, if you do it, you're going to be immortal. So thank you to the 500 some people that are already there, regardless of whether or not you're interested. I'm assuming you're not, but in case you are, whatever. Regardless of that, thank you for making it, 40 fucking minutes deep into a tutorial about paper. It's pretty lame. Should be doing something better on a Friday night. See ya.